So the title of which is Yukawa interaction against black hole backgrounds, and from an exterior EFT or effective field theory perspective. So as you can see, just the outline is just about the title. The first I'm going to talk about Yukawa interactions and black holes, just to set up a few notations and the background details, and then I'm going to directly go into the what do I mean by exterior effective field theory in the special case of Yukawa interaction, and then I will conclude with some remarks. So let's start with basic ingredients which we have for this talk. What is Yukawa interaction and black holes? So for us, Yukawa interaction is just interaction between fermions and bosons with the following interactive Lagrangian, where lambda is coupling constant, phi is a scalar which represents a boson, and psi is a spinor which represents a fermion. And as you can see, this interactive Lagrangian can give rise to these kind of Feynman diagrams, which are not, which in this case is like a 4-point diagram with one exchange. The dashed line represents the scalar, the solid line represents the fermion. And this is just usual Feynman diagrams which we study in the usual standard quantum field theory. We know in flat space-time that scattering amplitudes can be derived from using these Feynman diagrams. And the important ingredients to remember in order to draw diagrams or calculate scattering cross-section or amplitudes, there are three main ingredients: the external line, the internal propagator, and the interaction vertex, which you can see from the diagram also. These four solid lines in this diagram is external x, and the internal dashed line is called internal propagator, and there are two interaction vertices over there. So these are the three main ingredients in every Feynman diagram. And in the position space, the Feynman rules are that for each internal line, put a e to the power ipx, a plane wave, and for each internal propagator, we need some Feynman propagator, and for each vertex, there is an interaction vertex and an integral over space-time. So with this Yukawa interaction background in mind, let's take what black hole means to us. For this talk, I'm just going to say that for us, black hole is a region of space, is a solution of Einstein theory of gravity, which says that space-time which has a region from which nothing can escape, called black hole. As you can see in this diagram, the dashed the dark region represents the interior of black hole, and the boundary of that region is just called horizon, with the horizon size represented by RH. And this was classical black holes. In classical black holes, nothing escaped from the horizon. But once you include quantum effects, it actually radiates, and the radiation is called Hawking radiation. So strictly speaking, black holes are not really black, because once you add the quantum effects, they will radiate according to certain temperature. And with these black hole and Yukawa interactions in mind, let's go to a basic problem that while Yukawa interactions and scattering has been studied in flat space-time well enough, but in the presence of black hole, it is not understood that properly. So let's see what are the tools we need to study these interactions in the presence of black hole. So in the presence of black hole, the main problem we have is how to deal with the interior of black hole. And our idea is to deal with interior is just forget about interior at all, and just write the field theory about outside the exterior of the black hole, which we sometimes we are calling exterior EFT. By exterior EFT, I just mean that an effective field theory which is written in the exterior of the black hole. And this circular diagram over here represents the radial direction. R is increasing in radially, and the origin is actually replaced by the horizon. And RC is just the cutoff in the radial direction. So you can see this diagram represents the exterior part of the black hole geometry. Interior is completely removed from here. And similarly, this diagram can be represented in another way also, where this line is a boundary cutoff, the gray line is the horizon, and the R is increasing upward. So from now on I will use both of these diagrams equivalently, because both of them represent the same thing. Both of them does not have interior in it, and both of them called a black hole exterior. To give a prototypical example of that, I will just take a 3-point function, and 3-point function will look like this. There are two solid lines and one dotted line. Again, the dashed line represents the scalar boson, and the solid line represents fermion. So this is a 3-point contact diagram, which you can either see from the circular picture or this planar picture. Note one thing, that the point where in the interaction vertex is always in the exterior of the black hole, because there is no interior in the diagram. That's why all the vertices are going to be in the exterior of the black hole. So this was just an example. So let's put, and now once we have set up what exterior EFT means, we need to write Feynman rules for exterior CFT, because we have now ignored the interior. So we need some rules which captures the effect of interior and still return in the exterior of the black hole. So for us, exterior EFT can be returned by modifying the usual Feynman rules. So note that I have already said that in Feynman rules there are 3 main ingredients: the external legs and the internal propagators and the vertices. So let's come to the external legs first. These are the external legs. The dotted line represents the bosons. And note that I have divided these external legs into 2 parts. Earlier there was only one external leg. Now I have 2 external legs, one with a triangle downwards, one with a triangle upwards, and which is saying that one is an outgoing propagator which is going towards the boundary, one is an ingoing propagator which is coming from the boundary, and these are called boundary Debug propagators. And these are analogous to external legs in the usual rules. And there are internal legs. The internal legs join one bulk point to the other bulk point. And again, I have divided these internal legs into 2 parts. One is retarded propagator, other is advanced propagator, and the triangle direction is a convention over here. And now, I mean, these are just for scalars. You can write down the same thing for the fermions also. For fermions, we will have again the ingoing, outgoing propagator and retarded and advanced propagator. So similar set of propagators or lines should exist for the fermions also, but I'm not going to write them down because they are very similar to these. Finally, there are vertices, and note that because there are many more vertices now. And earlier there was only one vertices, which was I lambda, and now it looks like there are 4 vertices now. And I will come to the factors later, but there are 6 vertices because there are 4 vertices now over here. But it should be 6 because every leg can take 2 values. Either it can be a triangle or a line, which you can see from here that if it is this line, it can either come to an interaction vertex with a line or a triangle. So every leg has 2 possibilities, and 2 into 2 into 2 is 6. So there are 6 possibilities. Out of 6 vertices, we find that 2 of them are just 0 from the thermality of the black hole and the unitarity. So there are 4 vertices, and note that in these 4 vertices, these Bose-Einstein factors and the Fermi-Dirac factors are coming naturally, which captures the effect that the black hole is thermal, and you're ignoring the interior of the black hole. So somehow the effect of the interior of the black hole is coming under the vertices of the Feynman rules, this new Feynman rules. So with these Feynman rules, now you can actually write 4-point function, for example, and these are the 4-point function. Again, I'm only drawing some few diagrams over here. You can draw many more diagrams, Feynman diagrams. You can draw 3-point, 4-point, 5-point. Even at the 4-point level, there are many more diagrams like this. But I'm just taking it to example. One with an fermionic exchange, one with a bosonic exchange. So all of these diagrams one can use Feynman rules and then write down scattering amplitude just as we do in the usual quantum field theory, and then obtain the scattering cross section and other objects. So this is the basic thing we have. Now I will try to conclude, because once you have the Feynman rules and establish of exterior effective field theory, you can do what we generally do in the quantum field theory standard textbook and obtain other physical quantities. So let me just conclude and with some remarks. So what we have done is we have developed an exterior. By exterior, I mean the exterior of the black hole. By ignoring the interior of the black hole, exterior effective field theory to model Yukawa interaction in the black hole background. And along with it, we also developed the corresponding diagrammatics. By diagrammatics, I mean the Feynman rules and the propagators, and accordingly how to calculate these amplitudes and all, and which naturally incorporates the effect of black hole. Remember that we don't have interior of the black hole. We are just working in the exterior of the black hole, and still we have the effects of interior of the black hole or the black hole in the interaction newly defined interaction vertices. And while we can calculate the amplitude to any order, we have limited our analysis, and at least in this talk, to only 4.3 level diagrams. I mean, one can go on and ask what happens at the group level or the higher point function. We can do that, but the whole analysis will, we hope that naturally go through, but we are not doing that here. So with that, I just want to make one more comment that there's a principle which Rajesh also talked about the day before, on the first day, that the gravitational problem in a specific scenario has a dual problem in the QFT side. And what is the dual problem of our setup? The dual problem of our setup is if you are given some strongly coupled holographic system, preferably which has fermionic degrees of freedom in it, how to find correlation functions there. So that's a dual problem. And we have an answer to the above question by studying the open effective theory by holography. Because if you can ask that question, you can convert that question into gravitational problem, and gravitational problem we know how to solve it. So that's the, I mean, you can motivate the same problem with the holography also. Last, I would like to tell you what two things which you need to remember if you are interested in holography. That this exterior EFT which we found in the gravity is kind of related to open effective field theory in the dual problem. And the Witten diagrams, so forget about Witten diagrams, but the diagrams which we draw just right now in gravity are kind of related to correlators in the dual problem. And this is a kind of invitation, if you want more details on this dual theory perspective, you can check out the poster which Godwin is going to present today, and which title of which is Open Effective Field Theory for Interacting Fermions via Holography. Or you can check out this paper if you want. Thank you. Yeah.
Could you just go back to this vertices that you, yeah. So how should I understand this appearance of these occupation factors in the vertices?
Okay, so one should first of all expect that if you are ignoring in the interior of the black hole, and black hole is a thermal object, it is radiating thermally. And so one should expect that somehow, somewhere the thermal nature of the black hole should reflect in the diagrams, because you're only integrating in the exterior of the black hole. You're kind of ignoring that, right? So the idea is that somewhere the Bose-Einstein factors or the Fermi-Dirac factors should come out naturally, and there is a prescription. Okay, this right now it looks like this is an ad hoc procedure that we are putting by hand, but it is not coming by hand because we have a prescription behind it in the gravity, which I have not explained over here. Probably, yeah, okay, I will explain it to you later. But this factors comes out very naturally in the end, and these are, I mean, from that prescription, the prescription is basically is a kind of how to write down this real-time geometry of which is dual to Singer-Kelly formulation. So there is a prescription behind it, and once you integrate out the interior degrees of freedom, you will get this extra factors which is supposed to be attached to interaction vertices. So I mean, it's okay. Right now, I'm just quoting the result, but there is a series of steps behind it, which I haven't gone through.
I see.
But just from the basic argument that if you are ignoring something about the black hole, then black hole effect should come out in the effective theory in the end.
Thanks.
Maybe can I just add one comment to that? That if you just take just a usual field theory in the finite temperature, Yukawa theory at finite temperature, just in flat space-time, and go to a thing where retarded and advanced propagators are the propagators, that everything in terms of retarded propagators, then you usually get these kind of factors in the vertices.
Should I compare in case of finite temperature usual?
You'll get all these diagrams and all these vertices. If you do real time, you have to do this double Schwinger calculation.
Okay, fine.
And one important thing I actually forgot. These factors actually are coming because we are drawing the diagrams in terms of retarded and advanced propagator. If you choose some other propagators, then the factors will also change accordingly. So this is, I mean, yeah, this is a kind of this is in a sense, it's the factors are coming because we are working with the retarded and advanced propagators, not like earlier. In the usual textbook case, we worked with Feynman propagators, which is different.
Okay. Can I just say something? So, is there a limit where these renormalized propagators, I think in Matsubara space, would boil down to what are called thermal masses? So basically, the boson becomes incoherent at some temperature T, so it does not remain really really coherent or gapless to arbitrary low energy scale, but it acquires a sort of mass which is proportional to temperature of the system.
Okay, I don't think I completely understand the question, but okay, the question you're asking, is there a limit where these propagators becomes just kind of gapless excitations of
No.
system?
Gapped by the effective temperature that is there.
That, okay, probably, okay. I would assume that in some low temperature limit, it would behave in that way, but I'm not completely sure that it happens.
Thank you, Shivam, for the talk.